Hi everyone, my name is Renae Geier and I am a member of Arm & Hammer Animal and Food Production in Waukesha, Wisconsin. Today I'm going to present to you a project we have looking at transmissible antibiotic resistance genes present in E. coli and Salmonella from USA poultry. I'd like to acknowledge Tim Johnson from the University of Minnesota for his help with this project. Since 2013, there has been a dramatic decrease in the amount of antibiotics included in broiler feed in the US. In 2013, 47% of broiler feed contained full spectrum antibiotics, and only 4% of broiler feed was no antibiotics ever. But as a result of consumer pressure and the veterinary feed directive, this pattern has flipped. And now in 2019, 58% of broiler feed is no antibiotics ever, and only 3% is full spectrum antibiotics. We wanted to know how this shift in antibiotic use was affecting the antibiotic resistance genes encoded by E. coli in these poultry guts. At Arm & Hammer, we have something called the Microbial Terroir Program, where we characterize pathogenic bacteria from small intestinal samples. Over 5,000 broiler and over 3,000 turkey guts have been analyzed since 2014. What we do is we have necropsy sessions where we then enumerate and isolate E. coli from the small intestinal tract, and then go on to characterize these E. coli for virulence genes using an APEC Multiplex PCR designed by Tim Johnson. We wanted to do whole genome sequencing on these E. coli to get a good idea of what antibiotic resistance genes they encoded. So we picked 111 E. coli isolated from poultry in the United States between 2014 and 2015. Most of these E. coli were from broiler guts, but we also isolated E. coli from broiler breeder, turkey breeder, and infected tissue guts. Also, most of them were APEC, but we also had commensal E. coli included. We did whole genome shotgun sequencing on them using an aluminum MiSeq. We then assembled the genomes using spades and annotated the genes using PROCA. Then of these genes that were annotated, we identified which ones were transferable antibiotic resistance genes using ResFinder and BLAST-P. We then classified each of these antibiotic resistance genes by classes. So the table on the right shows the major poultry veterinary antibiotic examples for each of these classes. And you can see that in E. coli, most of the E. coli isolates, more than 70%, had resistance genes to aminoglycosides. There was also a high amount of tetracycline and sulfonamide resistance, but there was also penicillin, fosfomycin, trimethoprim, phenol, and macrolide resistance. We did not see quinolone resistance in these E. coli. We then looked at the proportion of E. coli carrying resistance genes to multiple antibiotic classes. So in the left side of this figure, you can see that for the broiler isolates, we've characterized each isolate by the number of antibiotic classes that it is resistant to from 0 to 7. And 66% of these broiler E. coli were resistant to multiple antibiotics, which is characterized as 3 through 7 classes. Turkeys generally were resistant to more antibiotics. 92% of the turkey isolates were resistant to multiple antibiotic classes. We then designed a multiplex PCR to detect antibiotic resistance genes in the E. coli isolates without having to do whole genome sequencing. So we targeted 7 different genes that we found in these genomes from 6 different antibiotic classes. So DFR A14 from the trimethoprim resistance class, TET-A, which is a tetracycline resistance gene, AAC3VIA, which is an aminoglycoside resistance gene, APH31A, which is an aminoglycoside resistance gene also, beta-lactams, which is a penicillin resistance gene, MPHA for macrolide resistance, and SUL1 for sulfonamide resistance. To the right, you can see a multiplex PCR example gel which shows all of the E. coli amplicons for these genes. We went back and looked at E. coli isolated from poultry over time, so from 2015 to 2019, to see if there was a change in the amount of antibiotic resistance genes in these E. coli isolates. And there was a decrease. In 2015 and 2016, the isolates mostly contained more than 2 resistance genes of these 7 per genome. And then in 2017 to 2019, there was a decrease in the number of hits from the multiplex PCR, down to just over 1. And this was a statistically significant decrease. On the right, you can see a figure that shows the breakdown by individual gene. So in 2015, you can see that there's more resistance than in 2019. Most of these genes actually are decreasing over time, although there is some variability. We did not detect MPHA very often, which is the blue line at the bottom. And in addition, we didn't see DFR-A14 for trimethoprim resistance very often. That is the green line at the bottom. The most common gene that we identified was TET-A, the orange line at the top. Then we wanted to know, are the antibiotic resistance patterns similar in Salmonella enterica? So we did genotyping of avian Salmonella enterica isolates that were isolated from poultry in the United States between 1997 and 2017. We looked at 269 different genomes that we downloaded from a public database, Patrick. We then applied the same methods as the E. coli isolates. We annotated the genomes using PROCA and looked for transferable antibiotic resistance genes using ResFinder and BLASTP. Most of the isolates included here were also broiler isolates, but there were turkey Salmonella as well. And the serotypes of the Salmonella is shown in the pie chart. So primarily the Salmonella were Typhimurium, Kentucky, or Heidelberg, but there was a variety of other serotypes included as well. So again, we classified all of the resistance genes by these major classes. And these Salmonella, although they had very similar resistance patterns as the E. coli, they did encode more aminoglycoside resistance genes, as well as more fosfomycin resistance genes. Overall, though, per isolate, they contained fewer resistance to fewer classes. So the broiler isolates, only 47% of the Salmonella were multiple antibiotic resistant, about 20% lower than the E. coli that I showed you earlier. In turkeys, again, this was greater than the broilers. 66% of the Salmonella isolated from turkeys were multiple antibiotic resistant, but this is again lower than the E. coli, which was 92%. This figure shows each individual antibiotic resistance gene that we identified in the genomes of the E. coli and the Salmonella. Indicated by an asterisk are the genes that are included in the multiplex PCR. So we want to know, is the multiplex going to work on these Salmonella as well? And in general, it seems that they do share a lot of the same genes. So the aminoglycoside resistance genes are shown first on the left side, and there are a lot of different genes that we could target. One of the Salmonella genes that we might want to include in the multiplex is AAC6'1AA, which is the orange bar that goes all the way up to 100. So 100% of the Salmonella encode that gene, but 0% of the E. coli encoded it. But for the most part, they do all contain a lot of the same genes. So both E. coli and Salmonella encode beta-lactam, MPHA, SAL1, TET-A, and DFR-A14, but the prevalence differs slightly. So in conclusion, in E. coli, about 70% of broiler isolates and about 90% of turkey strains carried resistance genes to multiple antibiotic classes. In Salmonella, the isolates generally contained fewer total antibiotic resistance genes, Only 50% of broiler isolates and about 70% of turkey isolates carried resistance genes to multiple antibiotic classes. We developed a multiplex PCR to detect transmissible antibiotic resistance genes in USA poultry E. coli and saw a statistically significant decrease in the number of genes over time. Based on the genomes, the resistance patterns of the individual antibiotic resistance genes differ slightly between Salmonella and E. coli. Next, we want to do more whole genome shotgun sequencing to see if there's any diversity that we missed, and also run the multiplex PCR on more E. coli and Salmonella over time to see if the trends continue. And there is actually a continuing decrease of these antibiotic resistance genes as a result of decreased use. And with that, I would like to thank you for the time you have given me today, and I look forward to getting questions from you later in August. Thank you.